after learning about the basics of nuclear reactions, let's see what is a radioactive decay series. We have a sequence of radioactive nucleus decays when the first one decays to the second one, to the third one, to the fourth one, and so on until they form a non-radioactive element. 3 radioactive series are found, and you can, I'm not going to repeat, I'm not going to draw it because you have a beautiful diagram on slide number 39 of your book. The radioactive decay series for uranium-238, you'll have it there, which ends in lead-206. So decay after decay after decay, so, and most of them, all of them are alpha and beta particles. So it changes to finally lead-206. Now let's focus on the example on page 40 and on slide 40. You have 2 samples of water, each made up of different isotopes of hydrogen. One contains hydrogen 1 and one contains hydrogen 3, and both of them have 1 proton. Would you expect these 2 water samples to be chemically similar? Yeah, because in the isotopes we have similar chemical properties. Would you expect these 2 different water samples to be physically the same? No, because hydrogen 3, the water has more mass than hydrogen 1. So if you have H2O with hydrogen 1, it will be different than hydrogen 3 in the water. So this one will be heavier, more mass. And finally, the question is that which one of these water samples would you expect to be radioactive? This hydrogen 3, or we call it tritium. We call it tritium. You can expect it comes from 3. Tritium, because of the ratio of N to Z. It's more than when you have 1 on 1 than 3 to 1. So it's more likely to be radioactive. Okay, now it's time to talk about nuclear bombardment reactions. Very interesting types of reactions, nuclear bombardment. Its name says that there is some bombardment, but on the atoms. Nuclear bombardment reactions. So they're not spontaneous, they need an initiator. They involve the collision of nucleus with other particles, either another atom or other particles. Then there is something happening called transmutation. Change of one element into another by bombarding the nucleus of the element with nuclear particle or nuclei. So the process of changing one atom to another atom by emitting the particles or atoms is called transmutation. Change of element A to element B by bombarding with another atom or atomic particle. Examples. There are some examples given to you, like for example, you have nitrogen and you hit some alpha particles to it. You will end up having oxygen 17 and you will have proton. Or you'll have, for example, these are just the examples given. So in the exam, you're responsible to determine if you have any missing particles. If you bombard beryllium with helium, then you will have carbon. And can you tell me what particle is going to be also emitted? 4 and 9 is 13, but you only have 12 here, so you need the 1 in here. 2 and 4 is 6, so you need the 0 here. So what is the element? What is the particle? Neutron. And you also have aluminum and phosphorus. So for aluminum, if you bombard aluminum with alpha particles, aluminum is 27 and 13, and you bombard it with alpha particles, then what if we tell you there is a phosphorus with 15 and 30 atomic number and atomic mass? So 15, 2 and 13, 15. So the other particles should not have any atomic number, any protons. And 34 and 27 is 31, so it should be 1. So it's another neutron emission. Then phosphorus, 13 and 30 and 15, it emits a positron. This is positron. Let's determine the other atom. 30, we have 0, so your atom must have a 30 as atomic mass. You have 1 here, you have 15 here, so you need 14 more. Which element is element number 14? It's silicon. So that's how you guess the missing particles or atoms. Now, the next thing is to how to write down the abbreviated notation from the nuclear equation. Notations or abbreviated, how to write abbreviated notation from nuclear equations. For example, let's say we are given this equation. We have this equation, nitrogen is bombarded with an alpha particle. Each time you see helium, it should remind you of alpha particle. Oxygen plus a proton. So you will write down the actual atoms. Okay? The first atom was 14 and 7. Put parentheses and close the parentheses. The other atom, the other atom is oxygen. Put oxygen 17 and include the particle that bombarded first. Helium was on the nitrogen side, right? So it has to be closer to nitrogen in its notation. And what particle do you have here? Or instead of helium, you can also write alpha, okay? And here you have proton. So, or you can write it as proton. So you can write it so one more time. When you have an equation, you're going to change it to a notation. You will write the atoms, the actual elements. The one on the left side as a reactant outside parenthesis, then open the parenthesis. Write down the particle, if there is any particle next to it, first with a comma. This comma should be here. And then the particle on the product side. And close the parenthesis, and the atom as a product should be sitting outside. Because we are working with the abbreviated forms, let's learn some abbreviated forms now. Instead of neutron, we just put lowercase n. For proton, as you saw, we put lowercase p. For deuteron, which is hydrogen 2. Instead of no neutrons, it has one neutron. So you show it as lowercase d. And alpha particle, as I told you, which is helium 4, you show it as alpha. So these are good for also beta. You need them for writing the abbreviations. So on slide 48, you have a question. Sodium 22 is made by bombardment of magnesium 24. So magnesium 24, we check with the periodic table, its atomic mass is 12. Is provided by bombarding magnesium, the most abundant isotope of magnesium, with deuterons. Deuterons is, we said, hydrogen. Hydrogen has how many protons? 1. And deuteron has 1 neutron. We have it here. So it forms, sodium 22 is formed by it. Sodium 22, and we check with periodic table, it has 11 protons. So what would be the next particle? An alpha particle is the other product. 2 and 24 is 26. You just have 22 of them here, so you need the 4 here. And 12 and 1 is 13. You have 11, you need 2 more. So how to write the notation, the abbreviated form? We said we put the atoms outside. This is the first atom. This is the first particle. D for deuteron, right? Comma. What is the other particle on the other side? Alpha. And then you put the next element. So you need to have enough practice. If we give you this, you should be able to write the equation also. You can work on the next example. So for the bombardment, we said bombardment for the radioactive decay, we said it's a non-spontaneous reaction. So you put the particle, you have a good picture on slide number 52. You call it a cyclotron. They, as if I know how to draw it. Okay. Now, you enter there is a center. You enter the particles here, enter. The particles start, this is called the cyclotron. The cyclotron. So it accelerates the particles. It is composed of 2 D plates. They look like a D. And then the atom starts getting the acceleration, and then it comes out from the exit of cyclotron, and then it hits your target and does the bombardment. This is the target. So you cannot expect to put 2 radioactive elements next to each other or a particle next to an atom and expect them to something happen. You first need to accelerate, increase the speed and acceleration of the particle you want to or the atom you want to, put it in the cyclotron, and then hit it with a very high speed to the target. Then you will do the bombardment and the radiation occurs. But now after it hits the target, how do we measure the radiation? Radiation counters are two types of radiations. We're not going to do it, unfortunately. If you're we're going to go to the lab, you would have used one of the counters, ionization counters and scintillation counters. We used to work with the Geiger counter. You can read about Geiger counter. I'm not going to take the time of the video for it. Geiger counter is an ionization counter and a scintillation counter also. It's a little bit different, works a little bit different. What we need to do at this point to start working on some calculations. The activity of the radioactive source. Activity of a radioactive source or element, an atom, is the number of nuclear disintegrations per unit time that happens in a radioactive. So the number of disintegrations per unit time. And how to measure it by the unit Curie. Everyone has heard about Madame Curie, who lost her life studying the radioactive elements. Is the unit of activity 1 Curie is about to 3.7 times 10 to the 10. This is a constant which is given. 1 Curie is 3.7 times 10 to the 10 disintegrations per second. So every 3.7 times 10 to 10 disintegration per second is called 1 Curie. You know that we have a unit for every single quantity in chemistry. Remember mole, Avogadro's number? So this is Curie, but instead of saying 1, 2, 3 disintegrations, every 3.7 times 10 to 20, 10 disintegration per second is called 1 Curie. Then you can calculate the rate of radioactive decay, which is a first order reaction. You remember chapter 13 at the beginning of semester? Seems like a long time ago, huh? Rate of radioactive decay is rate constant times number of radioactive nuclei at time t. This is radioactive decay constant. Instead of rate constant, we call it radioactive decay constant. And it's the number of radioactive nuclei at time t. So it should remind you of a first order reaction. So let's work on an example. On slide 58, it's asking you the thorium-234. Thorium-234. decays by emitting a beta particle. So it decays by emitting a beta particle. A 50 microgram sample of thorium-234 has an activity of, so mass is 50 microgram, which is 50 times 10 to negative 6 grams, right? And it has an activity of 1.16 curie. What is the decay constant for this thorium-234? So what was the formula? Rate was K times NT, and we're solving for K. So we need to find N and we need to find rate first. How to find N? We know that our sample is 50 times 10 to negative 6 grams. A thorium 234 is 234 grams in 1 mole, right? And just like we said, 1 mole of everything is Avogadro's number. So 1 mole of nuclei, a nucleus is 6.02 times 10 to 23 nuclei. So N, these with this cancel. We want to find out how much nuclei we have left. The N is 1.298. This is what I have on the PowerPoint slides. Please check with your calculator. 10 to 17 nuclei. 10 to 17. Makes sense. The number makes sense to me. The next thing is to find rate. When you find the rate, because you have the number of disintegrations per unit time, you will use curie. So rate, you use 1.16 curie, and we know that 1 curie is, how much was it? 3.700, correct? Times 10 to the 10 disintegration. I just write disinteg. You will figure it out. Per second, right? So rate, basically multiply these two. Rate is going to be 4.292 times 10 to the 10 disintegrations per second. Now finding K is easy. So K is rate over NT, 4.292 times 10 to the 10 disintegrations per second divided by the number of nuclei, 1.298 times 10 to the 17 nuclei, and it will give you K as 3.31 times 10 to negative 7 per second. Got it? Okay, the next thing we need to know is the half-life. We said these radioactive elements constantly emit something. So half-life is the time when it takes for 1/2 of nuclei in a sample to decay. Half-life. Remember, we had half-life in chapter 13 also, and it was the time that when the rate of reaction was half of the initial. The concentration of the substances reached half of their initial concentrations. Now for half-life of nuclear reactions or radioactive elements is the time that takes 1/2 of nuclei in a sample to decay. The time it takes for of nuclei in the sample to decay. In the sample, depending on the elements, the half-life can be as short as seconds or as long as years. So again, because we're dealing with a first order reaction, so half-life, you remember what was the half-life for a first order reaction? 0.693 over K. That's the same exact formula for half-life. So first half of the compound, the nuclei is going to decay. Then after 2 half-lives, you have 1/4 of it remain. From the first half-life, half of it remains. The second half-life, 1/4 remains. The third half-life, 1/8, until you reach to nothing, 0. So the fractions remaining is 1/2, 1/2, 1/2, 1/2. And then if you have the mass over time, you will see it decaying as getting to 0. If you have 0 and the mass is 1, it reaches to 0 over time. Let's say you have 40 days for a specific sample. 40 days is not that much. Let's see what slide number 64 is asking us. Thallium-201 is used in the diagnosis of heart disease. The isotope decays by electron capture. The decay constant, K, is 2.63 times 10⁻⁶ per second. It's very short time. What is the half-life of this thallium-201 in days? We want it in days. So you have a formula here, very easy, plug and chalk. So K is 0.693 divided by divided by K. Let's talk first solve it for K. K is 2.63 times 10⁻⁶ per second. So T half-life is going to be 2. I hope it's correct, but 2.63 times 10⁻⁵, as it says. And we're supposed to change it to days. 1 minute, or let's say 1 hour, or okay, doesn't matter, is 60 seconds. 1 hour is 60 minutes. A day is 24 hours. So half-life in a day for this sample is almost 3 days only. So if you're working on it as an experiment, you need to hurry up. Within 3 days, half of it is gone. Question on slide number 66. Iodine 131 is used in the diagnosis and treatment of thyroid disorders. The half-life for the beta decay of iodine is 8.07 days. Half-life 8.07 days. We're supposed to find the decay constant in per second. And what is the activity in Curies of a 1 microgram sample? We start with finding K. K is easy because half-life is given, 0.693 divided by 8.07 days. You're supposed to find it in per second. So you do the opposite of what you did before. 1 day is 24 hours. And I would say just 1 hour is 3,600 seconds. So we will find K as 9.94 times 10 to negative 7 per second. Please check all the calculations with your calculator. Then we want to find the activity in Curie, and Curie is nuclei or disintegration per second. So we need to find NT, which is, because when you find Curie is the rate, right? The activity is rate, so 1 microgram, 1 times 10 to negative 6 grams. Then you have 1 mole of iodine is 127, almost 126.90 grams. Then 1 mole of nuclei is 6.022 times 10 to 23 nuclei. And then NT is going to be 4.745 times 10 to 15 nuclei. Then rate is, we found the rate constant, right? Is 9.94 times 10 to negative 7 per second times this, and T 4.745 times 10 to the 15 nuclei, and rate is nuclei per second, huh? Rate is going to be, or activity is 4.72 times 10 to the 9th nuclei per second. Then you can find out the percentage remaining by another formula that should look familiar. Do you remember this? Instead of N, you had A. Doesn't it look like the integrated rate law for the first order reaction? So N naught is original number of nuclei and NT is number of nuclei at time t. And K is the constant, NT over R naught is the fraction of nuclei remaining. Fraction of nuclei remaining at time t. So that NT on this slide number 69, I mean, it's I guess it's extra. It's been pasted by mistake. You don't need it. So let's move to slide number 70. I believe that's the last question. On slide number 70, a 0.500 gram sample of iodine 131 is obtained by a hospital. How much will remain after a period of 1 week? T is 1 week. The half-life of this isotope is 8.07 days. Half-life is 8.07 days. So first we need to find K, right? We need to find out the ln of NT over N naught. So let's find K. K is 0.693 over 8.07 days, and because T is in 1 week, so 7 days in 1 week. So the K is going to be 0.601 per week. And then we need to find ln of NT over N naught, which is minus 0.601 per week, right, times 1 week. So this ln is going to be minus 0.601 because you cancel week and week. And NT over N naught is going to be 0.548. So after 1 week, this is a fraction. If you multiply it by 100, about 54.8% is left, remain. And makes sense because the half-life is 8 days, 7 days, 1 week is almost close, but a little bit more than half of it is left. Okay, this is a nuclear chemistry chapter. We have more, but that's enough. You don't need to learn more than that, but make sure you work on enough examples to master this different topic of chemistry. Good luck.